escalator that's going down. Now imagine yourself walking up this escalator. As you walk up the escalator, you'll reach a point where your speed is equal to the escalator speed. That point is called dynamic equilibrium. You are neither moving forward nor falling back. Dynamic equilibrium is a concept that exists in both chemical contexts and in everyday life. This video will discuss dynamic equilibrium in 3 situations. 1. In a saturated solution, 2. In an unsaturated solution, and 3. In a supersaturated solution. First, let's talk about solubility.
Every solution has a maximum solubility point. This means there is a point where no more solute can dissolve in the solution. We refer to the ratio of maximum solute to solvent as the molar solubility of a substance. Let's look at a beaker filled with water. You are trying to dissolve salt into it. When more salt can be dissolved into the water, we call this an unsaturated solution. When the maximum amount of solute or salt is dissolved into the water, it is now called a saturated solution. If you add more salt than the maximum solubility point, it is a supersaturated solution, which means the extra solute or salt can leave the solution as a precipitate.
Now, let's look at equilibrium. What exactly is equilibrium? Dynamic equilibrium is a state of balance between forward and reverse reactions, or as seen in the escalator example, between the up and down motions. Reactants combine together to form products. At equilibrium, these products break apart to form their reactants. This is represented using this symbol. Dynamic equilibrium happens at a molecular level, so no change is observed at a macroscopic level, or by the human eye. There are 4 conditions that must be in place for a system to reach equilibrium. 1. It has to be a reversible process. 2. Macroscopic levels must remain constant, so color, temperature, conductivity all do not change. 3. It must be a closed system, therefore matter cannot escape. 4. It can be approached from either direction.
Let's look at a chemical reaction at equilibrium. How do we solve for the equilibrium concentrations? At 35 degrees Celsius, 2 moles of NaCl is introduced into a 2-liter beaker. At equilibrium, the concentration of NO is 0.032 moles per liter. Determine the equilibrium concentrations of NaCl and Cl2 at this temperature. So the first step is to write out the dissociation equation as seen over here. And next we're going to use a graphic organizer called an ice table as seen over here. Now I stands for the initial concentration, C is the change in concentration, and E is the equilibrium concentration. Looking at the question, we can see that we have 2 moles of NaCl in a 2-liter beaker, and this means that we have 1 mole per 1 liter, so we can write that in over here. We also know that initially 0 products are formed, so we have a concentration of 0 for both NO and Cl2, which we can write in over here. Also, we're given the equilibrium concentration of NO, which is 0.032, so we'll fill it in over here. And that means that the change in concentration for NO is a positive 0.032. And also, this is the only row where you can apply molar ratios. So applying that right now, we know NO and Cl2 are at a 2-to-1 ratio. So that means the change in concentration for Cl2 has to be a positive 0.016. We can also use this molar ratio to tell that the change in concentration for NaCl has to be negative 0.032, which leaves us with an equilibrium concentration of 0.97 for NaCl and 0.06 for Cl2.
In the mid-1800s, Goldberg and Wage developed the equilibrium law expression. They arranged the concentrations of the products and the reactants into this ratio, where K is a constant we call the equilibrium constant. The reaction quotient, called Q, is also used to arrange a similar expression. The only difference between Q and K is that Q is used for systems that are not necessarily at equilibrium. Let's look at the first situation. In a saturated solution, the chemical system has reached its maximum solubility point. No more solute can dissolve in the solution. In a saturated solution, the rate of dissolving is equal to the rate of crystallizing. Although K is used in the general equilibrium expression, we use the constant Ksp when describing the equilibrium specific to a saturated solution. Our expression now becomes, where Ksp is a solubility product constant.
For example, if we were looking at the dissociation of NaCl in water and we wanted to write the Ksp expression for this system, it would look like this. Since the concentration of solids and liquids are equal, they're factored into the Ksp constant instead. This means only aqueous and gaseous substances are included in the expression, leaving us with.
So why is KSP important? What is it used for? Comparing KSP to Q tells you two things about a solution: whether or not a precipitate forms and the type of solution. Is it saturated or not? The KSP of a substance is a given value, but in order to compare KSP and Q, you need to first calculate Q. In a saturated solution, KSP equals Q.
In 1884, Henry Louis Le Chatelier developed the Chatelier's principle, which states that when a system at equilibrium is disturbed by a change, the system shifts to oppose the change. In other words, when you take away reactants or products, the system shifts to replace what was taken away. Likewise, when you add reactants or products, the system shifts to use up what was added. Shifting the system right forms more products, and shifting the system left forms more reactants. A system at equilibrium can be disturbed by a change in concentration, temperature, or pressure. For example, if you increase the concentration of the reactants, the system shifts right towards the products to use up what was added. With regards to temperature, when you add heat, the system shifts in the direction opposing the energy. For example, in an endothermic reaction, when heat is added, the system shifts towards the products. If the system is cooled down, it shifts in the direction of the energy, in this case towards the reactants.
Let's look at the second situation, unsaturated solutions. In an unsaturated solution, the solute completely dissolves, leaving no remaining substances. Although a few molecules can form, there are not enough of them to form a solid, so no precipitate is produced. In an unsaturated solution, the system shifts towards the right in accordance with the Le Chatelier's principle. Therefore, even though the system is at equilibrium, it may not appear to be.
Let's look at calculations. If 100 milliliters of 2.1 times 10 to the negative 3 moles per liter of lead nitrate are added to 50 milliliters of 0.0060 moles per liter of sodium iodide, will a precipitate form? We know that our KSP is 8.5 times 10 to the negative 9. So the first step is to write out our chemical equation, and from this we know that PbI2 is going to be our precipitate, and we want to check if that precipitate can form. So the first thing we do is write out what we have before mixing. We know that this is what we have for sodium iodide, this is what we have for lead nitrate, and we know that our total volume is 100 milliliters plus 50 milliliters, so 150 milliliters. Next, we want to calculate the concentrations after we mix. So if we look at our dilution equation, C1V1 is equal to C2V2, we know that the C2 concentration value will be equal to C1V1 divided by V2. So if we sub in the values for that, we can see that the concentration of our Pb ion after mixing is 1.4 times 10 to the negative 3, and our concentration after mixing for our iodine ion is 2 times 10 to the negative 3. Next, we're going to write out our dissociation equation for PbI2, which is the solid. Looking at that, we can write our Q expression, and since iodine has a coefficient of 2, it's going to have an exponent of 2. So after we sub in the values, we get a Q value of 5.6 times 10 to the negative 9. Now compare that to the KSP value you had, which is 8.5 times 10 to the negative 9. Since KSP is much greater than Q, we know that the solution is unsaturated and that this precipitate cannot form and will not form.
Let's look at the third situation, supersaturated solutions. A supersaturated solution has an excess of solute which comes out of the solution as a precipitate, meaning the rate of crystallizing is greater than the rate of dissolving. In a supersaturated solution, the system shifts towards the left in accordance with Le Chatelier's principle. Therefore, even though the system is at equilibrium, it may not appear to be. Sometimes, in rare occasions, one cannot see a visible precipitate. When the temperature increases, the salt being dissolved breaks apart into ions that float in the solution, and although they want to come together to form a precipitate, they are unable to because they do not have a surface to form on. This is why if you put a string in supersaturated solution, the dissociated ions will crystallize on that string.
Let's look at calculations. If 50 milliliters of 0.04 moles per liter of calcium nitrate are added to 150 milliliters of 0.08 moles per liter of aluminum sulfate, will a precipitate form in this solution? The first step for this is to write out the complete reaction. As seen here, calcium sulfate is our solid, and therefore we will be solving for this. Before mixing, aluminum sulfate has a molar ratio of 1 to 3, so therefore we must multiply 0.08 by 3 to get 0.24. The next has a calcium nitrate has 1:1, therefore we keep our concentration the same. Our V2 is a total of 200 milliliters that we will be working with. After mixing, we have to use a formula C1V1 equals C2V2. We must rearrange this to solve for C2. For sulfate, when we multiply our 0.24 with our second volume, 200, we get 0.18. And for calcium, do the same thing, we get 0.01 moles per liter. Moving on to our Q expression, calcium sulfate. A dissociation equation is stated here. We multiply the two concentrations to get 1.8. Let's compare KSP to Q. We see that KSP is less than Q. This means the solution is supersaturated and a precipitate. What happens if the solute and the solvent share a common ion? How does this affect the solubility of the substance? For example, let's look at the dissociation equation of MgCl2. Adding substance with a common ion like HCl to this equilibrium mixture means increasing the concentration of Cl ions in the mixture. This means the system shifts to the left according to Le Chatelier's principle. As a result, more precipitate, or in this case, MgCl2, is formed. And since solubility is the amount of solute that has dissolved into the solvent, and a common ion increases the amount of precipitate formed, the solubility of the solute, or in this case MgCl2, decreases. And so the effect of a common ion is that it decreases the solubility of salt. So how do we factor a common ion into our calculations?
So let's try an example. Given the KSP for calcium fluoride, which is 3.9 times 10 to the power of negative 11 at 25 degrees Celsius, let's calculate the molar solubility of calcium fluoride in a 0.2 moles per liter solution of sodium fluoride. We want to determine the amount of calcium fluoride that can dissolve into a solution that already contains fluorine ions. When looking at the dissociation equation for sodium fluoride, we can see the 1:1 ratio of fluorine ions and sodium fluoride, so the concentration of fluorine is 0.2 moles per liter. Now when we write out the chemical equation for the dissociation of calcium fluoride, we can set up an ice table. We know the initial concentration of the fluorine ions, which is 0.2 moles per liter. Because there is no calcium ions in the solution to begin with, the initial concentration of the calcium ions is 0. The concentration for calcium fluoride does not matter because it is a solid and is factored into the KSP value. We use molar ratios to find the change in concentration, so calcium is X and fluorine is 2X. Because the ions are products, the change in equilibrium will be positive. Adding the initial concentrations and change in concentration will result in the concentration of equilibrium, which is X for calcium and 0.2 plus 2X for fluorine. To make the calculations easier, we can check to see if X can be factored out of fluorine by using the 100 rule. X is negligible if the concentration of fluorine ions divided by the KSP value is greater than 100. If it is above 100, then we can assume X is very close to 0. But we can only make this assumption if X is being added or subtracted, not multiplied or divided. In this example, when we divide the concentration of fluorine by the KSP value, it is much greater than 100, so X can be neglected. The equation to solve for KSP is the concentration of calcium times the concentration of fluorine. When we sub in the values, we end up with this equation. Remember, we assume that 2X is negligible compared to the KSP. That's why it's not in this equation. So when we solve for X, it equals 9.8 times 10 to the power of negative 10. X equals the solubility of the calcium ions, which also equals the solubility of calcium fluoride because of the 1:1 ratio. So therefore, the molar solubility of calcium fluoride is 9.8 times 10 to the power of negative 10 moles per liter.